Hey everyone, so first we're going to start off with initial mechanical energy is equal to final mechanical energy. And right now I'm finding the heights. So initial height of the ball is going to be 3 meters. And then from there you have to use some geometry to find the final height. From there you can set up PEI equals PEF plus KE, and you set in the values for mass, gravity, height, velocity, and etc. Then, as we wait for me to write this super slowly, we are going to simplify all the values that we subbed in for MGH and then 1 half mv squared. And then from there, we are going to simplify the values further in order to isolate for the velocity of the ball at 25 degrees dropped, after it dropped 25 degrees. Then for part B, to find a total, we have to find both centrifugal acceleration and tangential acceleration. We know that F of c equals mv squared over r, which is equal to mac. When you cancel out the masses, you can isolate for AC and then substitute those values in. From there you get 8.28 meters per second squared. Then to find a tangential, you have to set up Newton's second law, F equals mass times acceleration. And we know that the only force acting for tangential acceleration is going to be F of gx, so mg sine theta equals ma tangential, and then you cancel out the masses. And then from there, you're going to substitute in your values and then isolate for a tangential. Okay. And then to find a total, you're going to do basically the Pythagorean theorem. So it's going to be radical AC squared plus A tan squared. And then from there, you can substitute the values that you found in the earlier parts of the video. And then from there we can simplify and we find that A total is going to equal 12.14 meters per second squared. Then for part C, to find angular acceleration, there's going to be a relationship between A tangential and alpha, and A tan is equal to R alpha. So you isolate for angular acceleration, and then you get 2.96 watts per second squared. And then for part D, we have to find the velocity at the time right before the ball hits the block. So we're going to set up basically mechanical energy again. So potential energy equals KE, since it's all the way at the bottom. And then you find that V is 7.668 meters per second. Then from there, you're able to also apply Newton's second law. So you know tension minus F of c equals ma, and then you isolate for T, and you substitute the values in that you know, and you isolate, and then you solve and get 52.92 newtons. And for part E, you set up linear momentum. So initial linear momentum is equal to the final linear momentum. And then here is me literally just writing it all out because you have to for FRQ, even though it's stupid. Anyways, so since the ball is the only object moving in the beginning, you only have the mass of the ball times VI, and then after that you set up the momentum for the block and the ball. But since it's elastic, they have two different VFs. And then after you isolate, you have to do conservation of energy. So KEI is equal to KEF. And then it will cancel out the 1/2, and I don't know why I canceled out mass for a minute, but you cannot cancel out mass, they're not all the same. And then basically you have to isolate the whole equation to find the f of the ball or the block, so that later on you can substitute the that equation into the initial equation that we had, which was the linear momentum equation, and you can see me copying and pasting the like the part of the equation where I found the V block, I mean, in order for me to plug it into the calculator and find intersection to find that VF ball is 4.8798 meters per second. And then here's me going back to linear momentum to find the next part of the equation. Not the equation, but to find the other missing velocity. So basically, we're just going to set up linear momentum once more, but now that we know VF ball, we're going to substitute in that to find the VF block. So here's me literally just doing algebra for low-key a minute. Okay, now that we're done with algebra, we find that VF block is 12.54 meters per second. And then for the next part, we have to figure out what our A is. So we set up f of k is equal to ma, because when the block is simply sliding on the surface, there's no force acting upon it except for f of k. So what we're going to do is we're going to find A, and we know that A is 1.568 meters per second squared. And then from there, we can use VF equals AT minus VI to find the time it takes for the ball to stop, which is 8.002 seconds. And then for part G, we're going to set up common form in order to isolate for delta x. And since we know that there is no VF because it comes to a stop, so VF is 0, we're just going to substitute all the known values in and find delta x, which is the distance it takes for it to stop. And then since we know that for the new system it's going to be 3/4 of the distance, we multiply by 3/4 to find the new delta x. From there, we can use common form once again to substitute in the new values to find the final velocity right before it hits the rod. So then we find that VF is 6.27 meters per second. And then from there, we know the angular momentum is conserved. So we treat the block as a point mass, and we put that equal to I omega, which is going to be the total moment of inertia times omega. So when we substitute all the values in, we find that omega is going to be 0.614 rads per second. And then moving on to part H, we know that mechanical energy initial is equal to the final mechanical energy. So we're going to set up mgh is equal to 1/2 I omega squared to find out the maximum height that the rod will go. After we substitute all the values in, we can then isolate for h. And then you can now see me trying to fit in the last two terms in the corner. When we isolate, we get 0.17 meters. And then for the last question, angular speed would decrease because, and only because, we know that angular momentum is going to be mvr equals I omega, and we know that the initial angular momentum is mvr, and since we go from 2/3 to 1/2, we are going to multiply by a smaller number, meaning that the initial angular momentum would be smaller. And if that isn't good enough explanation for you, Mr. Long, I also found out what the angular speed would be for the rod if you were to hit it at 1/2. So we would basically do the same process as before, but substitute it for 1/2 instead of 2/3, and you find that it is indeed